Yeah, good evening, good morning, everybody. So we'll start the subject of thermodynamics today. Before that, can you just confirm whether you are able to hear my voice and the screen is visible? Yeah, I see a couple of names who are in the maths class also. That's a good thing because you know my teaching style and how we go about it. But maths is different because it's a common subject for all branches. So we have to take some things which are not relevant for a particular branch and all those things. But overall, you know, since we have to cover every branch, we have to work like that. But coming back to these technical subjects, it is like easier to deal with because more or less, the syllabus is defined and you have an idea about what you are supposed to do. Okay, so we'll discuss this thermodynamics course for maybe next like 14-15 classes in total. And it's a very important topic because it forms the basis for your other topics, such as applications. There are certain subjects which come under the category of applications of thermodynamics. Do you know any such subjects? Anybody? If you know, you can just type it out. Let's see. Yeah, propulsion, gas dynamics. That is also there. Plus, IC engines is also there. Power plant engineering is also there. Uh, you know, refrigeration and air conditioning is also there. RAC. Okay, so it's there for many of the like this thermodynamics forms the basis for many of the other applications oriented subjects. Okay, so we'll see that we'll see those after the completion of thermodynamics. Okay, so before we start, so usually there are certain reference books that are followed. So for thermodynamics, at least for your gate exam, you can follow. Uh, See, first of all, you should follow whatever we are discussing in the class, the notes, because the thing is, if you go to any conventional book or something, uh, you know, they cover everything in greater details. So there, the conceptual understanding is more important, not the important topics for competitive exams. Okay. So first of all, you should stick to the uh, class notes and whatever practice problems that you have during classes, as well as some assignments will be there. And apart from that, if you want any references, there are some good books around. Okay, in India, usually we follow PKNAG. Okay, I hope you have studied PKNAG or some another book in your bachelor's. Okay, uh, have you read PKNAG book on thermodynamics? So you know, just for the sake of getting the idea what you guys are up to. Have you heard of this book by author PKNAG? Matisham says yes. What about others? These books are actually available online also. If you don't have them, you can buy them, but if it is too costly for you, you can download the PDFs also. These are widely available PDFs. But I'll just give you some references so that in case if you don't understand anything here, you can ask me, and even after that, maybe let's say later on you get some doubts. Okay, so in those cases, you can refer to these books. Okay, so this is a very commonly followed book in India by PKNAG. Okay. I remember one time, one of my friends, he was appearing for interview for a particular PSU after the GATE exam, and the interviewer was asking him. Basically, he asked him which topic you are comfortable with. He said thermodynamics and applications, and the interviewer asking him some questions on that. But after a point, I forgot which question, but there was a disagreement between the interviewer and the interviewee, the student. So the interviewer asked him, from where did you learn this concept, where they were disagreeing. So the student said he learned it from Pekenag book. So then the interviewer said he himself is the guy called as Pekenag. So the book is written by him only, and that's why he's not correct. The student is not correct. Okay, so such kind of things also happen. So anyway, that was just another incident that happened. Okay, so apart from this, there are some books by Moran, Shapiro and Sontag also. So I'll just note them down because these Moran Shapiro book is good for problems. Okay, these fundamentals of engineering thermodynamics. Okay, so thermodynamics, I will use this acronym TD, okay, because writing every time is a lengthy process. Okay, so this book is good for numericals, Moran and Shapiro, and it's numericals are also not that difficult, and somewhere online you will find the solution manuals also. Okay, so these two books are okay, and just for the sake of completeness, there is another book by Sontag, author Sontag, Richard Sontag. Okay. So it is also fundamentals of thermodynamics. By Sontag and Borganake or something. Let me just check. Yeah. So this book is by authors Sontag and Borganake. Okay, so this is also, I mean, like a Pekenag book, more on concepts, not on the numericals. But the Moran Shapiro is good for numericals also. Okay. So you can refer these books in future if you want to prepare something for your interviews or something like that. During the regular classes, just follow whatever I'm telling you, because I have read this. I read these books, and based on the important topics for competitive exams, only I'm teaching you some of them. Okay, because this thermodynamics is a very, very big topic. We don't need to study everything at this moment. Okay, so we'll study the basic building blocks, which will help you in different subjects. Okay, and more or less, if you consider the weightage of this subject in your GATE exam, typically speaking, for branches like aerospace, mechanical, and civil, around 10 marks on an average, 10 to 12 marks you can expect from thermodynamics plus its applications. Okay, some years it is less, some years it is more. So that's why an average estimate is given. Okay. For other branches, it might be on the lower side because their technical subjects are different. But for these branches, it is important topic. Okay. So with that, let's move on. And I think enough students have already joined. So shall I go to the next slide? See, if you have any doubts, you can ask in the chat box rather than speaking, and that will be easy to answer also. And otherwise, you can raise your hand, or those kind of things are possible. But don't keep doubts in your head. Okay, so whatever doubts you have, it is better to get clarified here only. If you make mistakes in the class, this is allowed and this is expected also, because this thermodynamics subject is widely taught but not taught correctly in many places. Okay, they just tell you some things and you are supposed to believe them. But at least in this class, you can ask whatever question you want. If I can answer, I'll answer. Otherwise, I'll get back to you, because this thermodynamics is more or less conceptual based subject. Okay, it's not like mathematics where you have formula and directly you'll get the answer. Here, there are certain things which you need to imagine or get the feel of. Okay, so sometimes not only me, even great professors also struggle in these thermodynamic subjects, who have been teaching these subjects since like quite a number of years. Okay. Anyway, so let's move on. Okay. So as the name of the topic today is the basic concepts, so we'll deal with certain basic things that you should know, and from the next class we'll start different things. Okay. Work interactions, heat interactions, first law. Okay. So before we move on, I'll just tell you the major topics that are there in the thermodynamics syllabus. So today we'll deal with basic concepts. Then there is zeroth law. Then there is first law. Then there are certain variations of first law, steady state, unsteady state. Then there is a entropy, very important concept. Based on that, you have second law of thermodynamics. and then you have something called as exergy or availability. Okay. After that, we study certain thermodynamic relationships, and then towards the end of the syllabus, we study properties of pure substances and properties of gases and gases mixture. Okay. So this is the whole syllabus. There are many more topics in thermodynamics apart from this, but you are not supposed to learn them at this stage. Okay. If you go for higher studies, then you study advanced concepts like fugacity, etc., etc. Okay, but will not go there in these classes because not required. Okay, so let's start. So the first question is, what is thermodynamics? Okay, so can anybody tell me what is thermodynamics, or any definition or any keywords that come to your mind? What is thermodynamics? Because these kind of questions they ask in interviews. Okay, maybe not in the GATE exam, but if you say in any one of the interviews, like, thermodynamics is my favorite subject, the first question that you should expect is, what is thermodynamics? How do you define thermodynamics? Matisham is saying flow of heat. Okay, that is one aspect of it. Anybody else? See guys, it would be better if you participate in the class, okay? Because otherwise it will be just me speaking, and that becomes monotonous after a point, and then you lose interest. Because these are online classes, I can't see your faces. I can't guess how much you are into the class or how much bored you are. Okay? So you have to participate. Mallikarjun is saying study of heat transfer. Then that is a heat transfer subject, no, Mallikarjun? If you are studying heat transfer, that's the subject of heat transfer. We are asking about thermodynamics because we study these subjects separately, right? Thermodynamics and heat transfer. The basic difference is thermodynamics deals with two states of your system, and heat transfer deals with how do you go from state 1 to 2 in a practical manner. Okay, so that is the difference. Heat transfer is always about the rate of heat change from state 1 to state 2, and it usually considers practical processes like sensible heat transfer and other things. But thermodynamics, or at least the classical thermodynamics that we are going to study, it deals with only initial state of the system and the final state of the system. In between, we usually consider it as to be a reversible process or quasi-static process. So we don't usually bother ourselves with the rate of change of properties. Okay, in one of the topics, that unsteady flow or unsteady condition of first law of thermodynamics, we'll see there. There we take some time derivatives, but there also, it is a very idealized assumptions. Okay. So sometimes this question is also asked: what is the difference between thermodynamics and heat transfer? Okay, so heat transfer basically deals with a rate of transfer of quantities like heat or work or any other properties like that. Whereas thermodynamics doesn't usually deal with the rates. It usually deals with between two states, initial and final state. Okay, and then it is our choice to assume how that system reached from initial to final state. Okay. Anyway, so the definition of thermodynamics as such is, it is a branch of science. It is a branch of science which deals with the study of energy interactions. Okay, so you can't just say heat, it can also be work, right? So basically what you are doing is you are studying different types of energy interactions. So this heat and work, the internal energy, all of them, they fall under the energy interactions between the system and its surroundings. Okay, so now this is a formal definition of thermodynamics. You may find this in many standard books. The language may be slightly different, but the idea is same. So whenever they want you to define thermodynamics, you are supposed to tell that it is a branch of science which deals with the study of energy interactions between a given system and its surroundings. Okay, this is a bookish definition, or if you want to score some brownie points in your interviews or something, you can also give the second definition that I like I came across this somewhere when I was preparing. This is not in any book or anywhere. It is like a clever way of putting everything together. Okay, so somebody can define thermodynamics as study of 4 E's. Okay, so there are 4 words starting with alphabet E, and those 4 words we study in the thermodynamics subject. What are those words? First is equilibrium. Second is energy. Then entropy, and then exergy. Okay. Someone may argue that why not enthalpy? Because enthalpy usually we encompasses in the energy term itself, because that is nothing but internal energy plus flow work. So it is nothing but kind of an energy interaction only. So therefore, no need to write enthalpy as a 5th E. It is assumed or subsumed in energy. Okay. So this is a unique definition that you can give, so that the interviewer also knows that you know what you are talking about. Okay. So then you are basically directing the interviewer to ask questions on these 4 topics. So you should be prepared about them also. So this is just a basic definition. If you have any doubts, ask me. Otherwise, let's move on, and then we'll define basic concepts like system and surroundings. Okay. Then system boundary. Okay. Shall I go to the next slide? Okay, so I hope the difference between thermodynamics and heat transfer is clear, because thermodynamics deals with the energy interactions between the system and surrounding, whereas heat transfer is one of the particular energy interaction. Okay, so for example, if you consider the set of energy interactions, okay, okay, that includes heat, work, internal energy. We'll see these things as we move on. And apart from that, there are some macroscopic energies also. For example, kinetic energy, potential energy. Okay, so all these energy interactions are dealt in thermodynamics subject. Okay, but there is a small subset of this which is nothing but heat interactions. Okay. Okay, so heat interactions are basically under the purview of subject of heat transfer. Okay, and these heat interactions basically we study between the like your system, but that is we basically deal with transient situations. Transient means time dependent studies, because we are dealing with the rates. Okay, so heat transfer is a different subject where the transient states of your system are important, whereas in thermodynamics we consider all kinds of energy interactions, including heat, work, internal energy, kinetic, potential, and maybe there are some other magnetic energy, etc., electromagnetic, all those things. But that is how you should define the difference between heat transfer and thermodynamics. Okay, and apart from the types of energy interactions, it's like the nature of the interactions that you study. In heat transfer, you study basically transient processes, whereas if you had solved any heat transfer, have you guys studied heat transfer subject so far in these classes? No, right? So when you'll study, you'll realize that all the problems that you solve, the units of your solutions are usually watts. Okay, so basically that is joule per second. So joule is the SI unit of energy. So basically, in heat transfer, most of the times you deal with the energy transfer per unit time. Okay, so that is why it is transient studies or rate of heat transfer. Okay, so these kind of hints are there. Whereas when you'll solve thermodynamics problem, most of the solutions that you'll have in terms of energy interactions, they will have units of joule. Okay, so basically we consider only the energy interactions, not the rate of change of energy interactions. Okay. So is this difference clear? If yes, let's move on to the next slide. Okay, shall I go to the next slide? Harsini is saying yes. So I mean, Harsini, do you understand the difference between heat transfer and thermodynamics now? Because this is also famous subject question in many interviews. They ask these things. Okay. So the next thing is what is system and what is surroundings, because we talk about system and surroundings all the time in thermodynamics. Okay. So therefore, let's say you are focusing on some region in the universe. Okay, where within this region certain energy interactions are going on. So this is called as your system, and whatever is external to your system, that is called as surroundings. Okay, it's a very basic definition. Some of you may think it is a trivial definition, but it's not, because depending on different type of problems, it is your choice to consider what is your system and what is your surroundings. Okay, and they are separated. They both of them are separated by something called as boundary. Okay, or system boundary also they will call in some books. Okay, so system boundary is a interface or the partition which separates system from its surrounding. Okay, so the system is formally defined as domain of observation or interest. Okay, and then you define something called as surrounding, which is nothing but everything which is external to the system. Okay, everything external to the system. Okay, and there is one last term which is called as universe. Okay, and universe basically means system plus surrounding. Okay, so this is like the total uh, space or total matter vacuum, not vacuum, total volume occupied by the matters. See, this is like our mathematics we studied is probability, the total sample space. Then there are two events, events A and events A complement. So basically the same analogy you can use. If your sample space is denoted by universe, your system is nothing but some event A, and surrounding is its complement, A complement. Okay, something like that you can also devise for your understanding. Okay, is this clear? We'll see more details about these things later on or subsequently. So right now, just giving you the definitions. Okay, so then there was one question in the previous years that they had asked on the system boundary. Usually they ask questions on system or surroundings, but there was one question where they asked about the system boundary. Okay, so you should know certain properties of system boundaries. Properties of system boundary, because we usually deal with the system boundaries which are fixed in nature, but it does not have to be that. It can be flexible also, or movable or stretchable system boundary also. So that depends on what type of problems you are solving. Okay. So first of all, system boundary can be real or imaginary also. Okay. For example, if you are dealing with the piston cylinder assembly problems, the casing or the cylinder, that is a real system boundary. But in many problems, you can define an imaginary system boundary also, depending on the ease with which you can solve that problem. Okay, we'll see those things later on, but you should know these things. Okay. And the second thing is it can be a fixed boundary or it can be a movable or stretchable boundary also. Okay, this movable or stretchable boundary we use when we solve problems related to balloon filling or balloon collapse, something like that. Okay, So in such cases, or some membrane is expanding. Okay, so in such cases, instead of assuming a fixed boundary, system boundary, we assume it to be movable or stretchable. Okay, and the third property is, it is considered to be of nearly zero thickness. Okay, so basically, this property is considered in order to uh, say that whatever interactions happen between system and surroundings, they are not affected by the or not altered by the system boundary. Okay, that is why we assume it to be a very thin, almost zero thickness boundary, so that this is basically done to assume that the energy interactions between system and surroundings or surrounding are not affected by the boundary. Otherwise, it will be very difficult to solve problems, because then you'll have to consider system boundary also as one of the component of your analysis, and it will be difficult. Okay. So these are some of the properties of system boundary. They had asked one question previously, so that is why you should know these things. They may repeat it. Okay. Any doubts? If not, let me know. We'll go to the next slide. Okay. So these are some basic things. Some of you may already know these things. Okay. So that's not the point. The point is, this is for all. So all the students present in the class should be on the same page when we start important things from the next class. So therefore, we are describing all the basic things today. Okay. Shall I go to the next slide if you are done with this? Okay. Then there are types of systems. Okay. So, since we talk about system, surroundings, etc., surroundings is more or less surroundings only, because there are no different types of surroundings. We usually consider it to be a body of infinite specific heat capacity and all those things. And we assume that the temperature of surrounding do not change temperature and pressure, because it's a vast or very big type of body. But when it comes to systems, we assume or we solve problems based on what type of system it is. Okay, so there are three types. First is called as closed system. Okay. Closed system. Anybody knows what is a closed system? There is one closed system, then there is open system, and then there is isolated system. Okay. So anybody knows what is a closed system? Yeah. No heat and energy. No, Matisham. That is isolated. In closed system, energy interactions are allowed, not the mass interactions. So heat and energy you are saying, huh? No. Yeah, no, mass transfer is the correct answer. Or mass interactions, not mass transfer. Okay. So the thing is, only energy interactions between system and surrounding are allowed or permitted, whatever you want to call, but no mass interactions. Okay, so that is the main thing. And interactions. And the second type is nothing but open system. Okay, so as the name suggests, it is open. So it is open to energy as well as mass interactions. Okay, so both energy as well as mass interactions are allowed. Okay, so between system and surrounding, I'm not writing that again and again, that you know, because we are dealing with interactions between system and surroundings only, right? So that is understood. Okay, so if I ask you piston cylinder assembly, because we solved those examples quite extensively in this course. So what do you think? Piston cylinder assembly is a closed system or open system? For example, I'll go to the next slide. Shall I go to the next slide? Yeah, noted this down. See, some of you are saying closed, some of you are saying open. The thing is, it's a tricky question, and many times this question is asked also. Okay, so the thing is, if I just say piston cylinder assembly, you should ask me the next question. Piston plus cylinder assembly, if I ask you whether it's a closed system or open system, you should ask me the next question, because this is not a complete information. Okay, so if there are no walls on the cylinder, that means you have something like this. You just filled some gas inside the piston and you closed it. Okay, so in such cases, you can have heat interactions, right, or even work interactions with the surroundings, but you can't have mass interactions. So in this case, this type of system becomes closed system. Okay, whereas if we have walls present on the cylinder, walls present on cylinder head or cylinder top, this happens usually in case of IC engines. Okay, because IC engine has exhaust and inlet valves. So in such cases, some of the processes are analyzed as closed system process, whereas some of the processes are analyzed as open system or open processes. Okay, so therefore, if somebody asks you what is this piston cylinder assembly, ask the next question: the walls are there or any openings on the cylinder are there? If not, then it is a closed system. But if it is having walls which open during the operation of the piston cylinder assembly, then it becomes open system. Okay, because through these walls, mass can go out or come in. Okay, so therefore it's an open system. Here also you will have heat and work interactions. That is also possible. The only difference is mass can also come in and go out. Okay, your piston cylinder assembly is your system here. Okay, and everything external to your piston cylinder assembly is your surroundings. Okay, so is this difference clear? If you understood this point, then this open closed system definition is more or less understood. Okay, any doubts, or shall I move to the next type? Okay, then there is a third system which is called as isolated system, and as the name suggests, it is isolated. Okay, so isolated means you don't have any interactions within system and surroundings. That means no mass and no energy interactions between system and surrounding. Can you give me one example of this? Any isolated system that you have studied or come across in your life, practical life? Anybody? Yeah, Bharat is saying flask, but see, even in the flask, after 6 or 8 hours, it becomes normal temperature, right? So energy interaction is allowed, no? Yeah, you should say perfectly insulated flask, okay, or thermoflask, whatever you want to call. Because if you just say thermoflask, it is not a isolated system because the insulation that you use, it still has non-zero thermal conductivity. So therefore, there will be some heat loss, very small rate, but there will be. So therefore, it should be denoted as perfectly insulated thermoplast. Such thing does not exist in real life, but just for the sake of argument, it is assumed to be isolated system. Any other example that you can think of apart from thermoplast? This universe, basically we define it as system and system plus surrounding. If you consider the whole universe, it is assumed to be isolated system. Okay, so in some exams they give this kind of options also. Okay, so keep that in mind. Universe is also considered as isolated system. Okay, so these are some types of the system. So shall we move to the next topic? Okay, so then before we move on, there is one slight this thing that you should know what type of thermodynamics we are studying, because thermodynamics is also having some classifications because it's a very big topic. So many times what we are studying today is called as classical thermodynamics. Okay, so if you consider thermodynamics as the main subject, it has some branches, and two prominent branches are the first is called as classical thermodynamics, what we are doing or what we are going to study in this subject, and there is another class of or another branch of thermodynamics which is called as statistical thermodynamics. Okay, this is usually taught in higher or advanced this classes. Okay, not usually for undergrad or gate exam. Okay, and what is the difference? Basically, classical thermodynamic deals with this energy interactions and work in whatever mass interactions that we study. That basically we consider to be average, deals with study of behavior of or average behavior of system molecules or particles. Okay, because your system will have certain number of molecules or particles. Actually, let's not use particles because that may be confusing. Let's talk in terms of molecules only, because everything is consisting of atoms or molecules. Okay, so whatever the material or the matter is there in your system, it will have certain number of molecules and atoms. So we study their average behavior. We don't go on individual molecular level to do the analysis. Okay, therefore it is also called as macroscopic approach, macroscopic or continuum approach. Okay, continuum means we assume that your the matter or the material inside your system is present locally everywhere. So that is why that is called as continuum. Okay, and macroscopic means we are studying the average behaviors. So therefore it is called as macroscopic approach. Okay, whereas this statistical, and this is what we are going to study. Okay, this classical thermodynamics is our focus of present study or present classes. Okay, there is something called a statistical thermodynamics, which is not that easy to understand, because here you study behavior of individual molecules or atoms of your system. Okay, so they basically study different particles, and based on them they do some statistical inference from those. Okay, so that is out of our syllabus, but it is also sometimes called as microscopic approach or a rarefied medium approach. Okay, you must have seen or heard this term rarefied gases theory. If you not, if you solve some problems in previous gate or ESE prelims, you'll see that they use this rarefied medium or rarefied gas concept. Okay. So rarefied means the matter of your system is not present at each and every local point. That is why it is called as rarefied. Okay. So have you guys studied fluid mechanics so far? Your batch has been taught fluid mechanics so far. Do you know Knudsen number? Okay, okay. But do you guys know Knudsen number? What is a Knudsen number? Any idea? Because usually, this Knudsen number is used to differentiate between the rarefied medium and the continuous medium or continuum medium. Okay. I'll just give you one small this thing formula for it. But the it is mainly discussed in fluid mechanics classes. Matisham, it's ulta. It's lambda by LC. Okay, so this there is something called as Knudsen number. Okay, usually denoted by Kn, lambda by L. Okay. Where lambda is mean free path of gas molecules or atoms, and L is nothing but characteristic length of your system. Okay. For example, if you are studying a flow of gas through a pipe, so the diameter or the radius of the pipe is considered as the characteristic length, usually diameter, whereas inside the pipe there are certain molecules, right? So on an average they will have certain mean free paths. Okay, you can quantify that. There are certain formulas. Based on that, you define Knudsen number, and usually it is defined for gaseous mediums only, because liquids are usually continuum. They satisfy continuum approach because the molecules are quite densely packed. Whereas in gases, as you reduce the pressure of the system, or if you increase the temperature of the system, this mean free path length increases, and therefore Knudsen number increases. So basically, if your Knudsen number is less than, let's say, 0.01, which means very small. That means your mean free path is very small as compared to the characteristic length. So in such cases, we use continuum approach. Continuum approach is valid. Okay, but there are certain regimes where you will have very high Knudsen numbers. Let's say greater than 10 or something like that. So in such cases, these are called as rarefied gas medium. Okay. Do you think of any application where we use this rarefied gas medium basis and then do some calculations? Can you think of any practical application where these kind of things will happen? Yeah, space. Because usually in the space or outer atmosphere, because the density of air keeps on decreasing as you go from the Earth's surface to the outer atmosphere. So, if you reach, let's say, moon or somewhere, there is no atmospheric air as such, right? There are no molecules of any gases present around the surface of the moon. So in such scenarios, you have to use the rarefied gas or rarefied approach, okay, or this statistical approach. Okay. So each and every thing has their own importance for a particular set of problems. Okay. But we usually don't deal with these things of space experiments, etc. in the GATE syllabus, so therefore we are not going there. We will study mostly the classical thermodynamics in this course, and for the most of your GATE syllabus, we study classical thermodynamics only. Okay. Any doubts? If not, let's move on. Shall I go to the next slide? So then, there is, apart from this classifications of system and types of thermodynamic branches, etc. Then we come to thermodynamic properties. Okay, so thermodynamic property. So can anybody tell me what is a property of a system when we call something as a property of our thermodynamic system? Yeah. Okay. So basically, uh, you know, uh, this property represents a certain characteristic of the system. Okay. So thermodynamic property is nothing but uh, it is nothing but a representation of certain characteristics of the system. Okay. Then there are two types of properties. Okay. Uh, First is called as intensive property. Intensive property. And other types of properties are called as extensive property. Okay. So very and sometimes instead of intensive, they will use something called as intrinsic. Okay. So in some books you may see instead of intensive they will use the term which is called as intrinsic. Intrinsic property. And in some books instead of extensive property they use the term which is called as extrinsic. Okay, so both of them mean the same thing only. No need to take any tension of this. It's just that you should know these are same terms. Okay. And it is very easy to remember this definition because it is in the name itself. Okay. So intensive or intrinsic property means that property will be independent of mass of the system. Okay. And extensive property or extrinsic property is dependent on the mass of the system. Okay. So this is the definition, and it is this definition makes it very easy. For example, if I tell you, if I ask you whether temperature is intensive or extensive property, temperature of the system, whether it is intensive or extensive property, intensive, right? And there is one very easy way to define this or find out these things. For example, you can do one thing. You consider your system, okay, something like this, okay, having mass m, and then you divide that system into two equal parts of having mass m by 2 and remaining mass of the second part is also m by 2. So if I ask you, whether the temperature of system is initially, let's say it is T, what will happen to the temperature of the system when you divide it into two halves of same mass? The temperature will still remain same, right? Because whether you have, total 1 kg of the mass of the system or half of kg, as long as they were initially at temperature, same temperature, finally they will be at same temperature only, right? So the temperature doesn't change when you change the mass of the system, and that's why it is an intensive property. Okay, so they sometimes ask these questions also. They will give you certain properties in the options and they will ask you to do these things, classify them as intensive or extensive. Okay, so Pressure is also intensive. What about density? Is density intensive or extensive? Intensive only, right? Because density, see, I'll tell you, density is nothing but mass by volume, right? So this mass and volume are both extensive. So there is a formula which says that ratio of two extensive properties are intensive properties. Okay, we use that, in a lot of places. Okay, so ratio of two extensive properties is an intensive property. Okay, so that's why see, mass and volume are extensive because when you halve the system, mass also reduces and volume also reduces in the same fraction. But if you take the ratio of them, the density, that will remain same because mass and volume both change in the same manner, okay, or by same amount or by same fraction. So therefore, this mass and volume of your system are extensive property, whereas density is the intensive property. And then there are certain properties like Cp, which is nothing but specific heat capacity, thermal conductivity. Okay, so these are all intensive properties. Hardness and many other properties are there, but you should just remember the fact that if you divide the system in half, whether that property changes or not. Okay, if it does change, then it is a extensive property, otherwise intensive. Okay, and then apart from that, in extensive properties, mass volume is there. Then you have kinetic energy, potential energy, total enthalpy, total internal energy, total entropy, etc., etc. Okay, so these are all extensive properties. But as I told you, the ratio of two extensive properties is in an intensive property. So what do? You define specific enthalpy, which is nothing but total enthalpy divided by mass of the system, right? So therefore, the specific enthalpy is always in kilojoule per kg. Similarly, you define small s, which is total entropy divided by the mass of your system. Okay, so therefore, the total energies are extensive, but if you define, energy per unit mass like enthalpy, specific enthalpy, or specific entropy, or specific internal energy, or even for that matter, if you define kinetic energy per unit mass, kinetic energy per unit kg, or potential energy per unit kg. So all these properties then become intensive properties. Okay, so as long as they are representing total energy or total work interactions, they can be considered as extensive properties. But if you divide them by the mass of the system, then they will become intensive properties. Okay, and that is because of this important formula or result. Okay, any doubts in this intensive and extensive property? Because many a times they have asked this question, match the columns, kind of. Okay, any doubts? Shall we move on to the next concept? See, I have given you some frequently asked quantities here, but there are many properties like hardness or what else is there? Roughness, all those things are there. Okay, so you should explore. There are multiple properties. You should explore them and try to categorize them into extensive and intensive properties. Okay, and after that, there is something called as thermodynamics equilibrium, okay, or thermodynamic equilibrium. Okay, we use this term extensively in our subsequent classes. We'll use it, but you should know what do you mean when you say thermodynamic equilibrium. Okay, so any system is said to be in a thermodynamic equilibrium with its surroundings. Okay, I'll just note it down only. Any system is in thermodynamic equilibrium with its surroundings if all of the following following conditions are satisfied. Okay, so that this thermodynamic equilibrium consists of three conditions. First is called as thermal equilibrium. Okay, this EQ superscript M represents equilibrium. Okay, so thermal equilibrium means temperature of your system and surrounding should be same. Okay, so thermal equilibrium deals with the temperatures. Okay, so the temperatures of your system and surrounding, maybe I'll write it in bracket. Okay, so thermal equilibrium deals with the temperature of the system and the surrounding. So if both of them are same, then it is called as thermal equilibrium. Okay, second condition is called as mechanical equilibrium. In this, we say that the system and surroundings are in the mechanical equilibrium if the forces or the pressure terms between the system and surroundings are balanced. Okay, and then there is third one, which we usually don't bother about in our GATE syllabus. It's called as chemical equilibrium. Okay, this is important for branches like chemical engineering, etc. For us, it is not that important. I mean, by us means other branches apart from chemical engineering. But you should know that there is something called as chemical equilibrium, and it basically deals with the balance of chemical potentials. Okay. Can you tell me any system which is widely known and which falls under the purview of chemical equilibrium? See, basically, when we study piston cylinder assemblies, etc., there are no chemical reactions happening inside the piston cylinder, right? But in reality, if you consider the example of IC engine, when you compress, something happens inside, right? Inside the piston cylinder, right? That combustion process where your fuel ignites and the chemical energy is released in the form of heat inside the piston cylinder, which makes the piston move away from the top head of the cylinder. So there, this chemical equilibrium comes into the picture for such cases, because very commonly studied chemical reaction is combustion process, because it is used everywhere in many applications. So if you are dealing with certain systems where chemical reactions are taking place, then to define the thermodynamic equilibrium, you should also able to prove that the system or the various species in your system are in chemical equilibrium. And to do that, there is a term which is called as chemical potential. So for every species in your system, you define a chemical potential. And then based on those things, you define the chemical equilibrium. Okay, so all these three, if your system and surrounding are in thermal, mechanical, and chemical equilibrium with each other, then only you can say that system and surroundings are in thermodynamic equilibrium. Okay, is it clear? See, based on this thermal equilibrium, we have zeroth law of thermodynamics, which we'll see in some time, or in the next class, depending on the time. Okay, because these things we study extensively going forward. And usually, when in our system there are no chemical reactions taking place, we don't consider the chemical equilibrium, because chemical equilibrium comes into the picture only if there are certain chemical reactions taking place. If there are all inert gases or no reactions are happening in your system, then you don't bother about chemical equilibrium, and then only you consider thermal and mechanical equilibrium to define thermodynamic equilibrium. Okay, so those parts are, I think, understood. Okay, and then there are some small definitions. For example, maybe I'll use the next slide. There is something called as thermodynamic state. Okay, because going forward we will use this term extensively. We usually call it as initial state, final state. Okay, but it is nothing but your thermodynamic state of your system. Okay. So what do you mean when you say thermodynamic state of a system? Is nothing but representation of condition of the system at a given moment based on its properties. Okay, so that is what thermodynamic state of a system means. Okay, so what is the condition of your system at the given moment based on various its properties? Okay, like temperature, pressure, energy content, etc., etc. Okay, because later on we use these terms like initial state, final state, equilibrium state, this what do you say, quasi-static state, etc., etc. Okay, so you should know what is the state. Okay, just a definition, nothing more than that. But there is one important topic which is called as pure substance. Okay, so now I'll take some miscellaneous topics. Okay, like pure substance, ideal gas equations, Gibbs phase rule, etc., etc. Because we use this also later on. Okay, because we study something called as properties of pure substances in one of the subtopics subsequently. So anybody knows what is a pure substance? See, this is not this purity or impurity concept. Okay, don't mix it up that if something is 100% pure, that is called as pure substance. That is a common language, okay, or layman's term to define pure substance. We are talking about pure substance in thermodynamics. Okay, so anybody knows what is a pure substance in thermodynamics? Anyone? It is okay if you are wrong, doesn't matter. If you know, you should answer. If you don't, then it's fine. I'll define it for you. Okay. So pure substance, there are two characteristics. Yeah, constant composition is one of them, but that's not the full definition. That is half of it. Okay. So pure substance needs to satisfy two conditions. First, as Matisham said, it should have constant or uniform chemical composition. Okay. Constant or uniform chemical composition. That is first condition. But it also needs to satisfy, or there is another condition which usually students do not think of. Okay, and it is independent of number of phases. Okay, that phases means this our liquid, gas, or solid. Okay, for example, if I consider just pure water. Okay, so pure water only has H2O as the chemical composition, so the first condition is satisfied, and it is only in liquid phase, so it doesn't matter whether there are liquid, solid, or gaseous phases present. So therefore pure water is considered as pure substance. Similarly, water plus ice, if this is your system, is it a pure substance? Water plus ice, can you consider this as a pure substance? See, this is where students get confused. If I give you a system like water plus ice, what students think is water is different, ice is different, right? But it's a pure substance. This mixture, water plus ice mixture, is also a pure substance because both of them have chemical formula of H2O, And as I told you, the second point, that you should not be bothered about the number of phases present inside the substance. Okay, so here water is liquid, ice is solid, but still it is a pure substance. Okay, uh, Harsini, is this point clear? It's not only you, but all of those who are confused in this. Because if I give you only single component, most of you will answer. But the confusion comes if I give you the mixtures like this. Okay, so in that case, if I give you water plus ice plus water vapor, so that is also a this thing. Instead of just water plus ice, if I give you water plus ice plus water vapor, this happens at the triple point of water. Okay, so that is also pure substance. And there is, if you consider dry air, it is also pure substance, because we usually consider dry air, that means it will have mostly nitrogen and oxygen, and there are certain gases, like CO2 and other greenhouse gases, but they are usually are very present in very small fraction, so therefore we neglect them. Okay, but dry air we consider as pure substance. Okay, these are all previous year questions. Okay, so that is why I'm giving you all these things. And there is one catch. Okay, so I need to write it on the next slide. So shall I go to the next slide if you understood this definition? Yeah, for that I need some space. For example, see, the thing is, let's say this is your system, and in your system if you have just water, that is a pure substance. But let's say you have ice also. Okay, this is ice and this is water. Chemical formula is same for both them. Both of them is same, which is H2O, right? But the thing is, water is in liquid state, ice is in solid state, right? So therefore, some of you may think that this is a example of two different substances. So therefore, it's not a pure substance. So that is why I told you this is not the definition as layman terms. Okay, this is a thermodynamic definition. So it needs to satisfy both of these. So first condition is satisfied because both of them have same formula, H2O. And you should not be bothered about whether it is solid or liquid or gaseous. As long as it is having same formula, chemical formula, and same composition, it should be considered as pure substance. Okay. Is it clear, Matisham? Okay, and then there is one note here. Usually they will give you one option which is called as atmospheric air. See, one option will be dry air and one option will be atmospheric air. And they will ask you whether this is a pure substance or not. So dry air is a pure substance, but atmospheric air is not a pure substance. And why? Because the water content or the humidity. Okay, the humidity content changes from place to place, or actually I should just write humidity content changes based on time and location. Okay, so if you are near seashore or any water body, river or something like that, the humidity will be higher there during most of the times. Whereas if you are at the dry place like Rajasthan or somewhere, the humidity is quite low. So therefore, atmospheric air, basically we treat it as uh, dry air plus water vapor. Okay, and this water vapor content changes. So therefore, we don't consider atmospheric air as a pure substance. Very famous numerical or not numerical, competitive exam question. Okay, so this is about pure substance. And regarding these pure substances, there is one rule called as Gibbs phase rule. Okay, so shall I go to the next slide? I'll define what is Gibbs phase rule. Okay, so this is called as Gibbs phase rule. Okay, there are some things that they ask from this topic as questions. Okay, so first of all, why do we use Gibbs phase rule? Okay, so this gives you a formula to determine number of degrees of freedom. Yeah, Harsini, it contains dry air plus water vapor or humidity content, which is typically denoted by relative humidity or just humidity, and that changes. So therefore, if you consider a big domain, okay, so locally as well as temporally, that changes. Okay, so therefore, water vapor content changes locally and temporarily. So therefore, it does not satisfy the first condition of the definition of pure substance, and we can't consider it to be pure substance. Okay, and about the Gibbs phase rule, it is used to determine number of degrees of freedom. Number of degrees of freedom for a system. Okay, number of degrees of freedom required to describe or fix the state of the system. Okay, now the question is, what is this number of degrees of freedom? So what is the definition of degrees of freedom? Okay, so this degree of freedom or degrees of freedom, you will see they use DOF as the acronym for that in many books or questions. Okay, it is nothing but minimum number of independent variables. The minimum number of independent variables, or you can call properties also, but by the definition it is minimum number of independent variables again required to describe the state of the system. Okay, we'll see that, but just hold on for a couple of minutes. I need to go to the next slide to define the Gibbs phase rule, and then we'll see what do I mean by degrees of freedom or independent variables. Okay, so this is about the use of Gibbs phase rule, and the formula, very famous formula, is nothing but P plus F equal to C plus 2. Okay, what are P, F and C? I need more space to express them, so shall I go to the next slide? Okay, so this formula is, see, first of all you are supposed to remember this formula, P plus F equal to C plus 2. In many books it is given as C equal to P plus F minus 2 blah blah blah, or F equal to C minus P plus 2, but I feel this is easy to remember. Maybe I can give you a memory hint. PF, you guys might have heard about PF, right? So you can remember, like, provident fund. I mean, this is just a memory trick, okay? It doesn't mean that it's a provident fund. But if you remember that on our LHS it is PF, then on RHS only C is there. Okay, so like that also you can remember. So this is like your memory trick. Because many times students forget whether it is P plus F, P plus C, C plus F on LHS. Okay, so if you don't want to forget, you can. I use this provident fund because that PF is easy to remember. If you have some other acronym for PF, you can use that also. Up to you. Okay. But what do these terms mean? Okay, so P represents number of phases in your system. So as I told you, phases means liquid, vapor, liquid, gas, or solid. Okay. F represents the degree of freedom or the minimum number of independent variables to describe or fix the state of the system. C represents number of chemically independent constituents or number of you know chemically independent constituents or components. Okay, and this constant plus 2, it also has meaning. It is not like arbitrarily you can put any constant. Plus 2 comes because we considered I mean, you have to go through the derivation, but the basic idea is we consider temperature as well as pressure of the system as the variables. Therefore 2 comes. Okay, I'll explain you, because in material science, if you study the carbon carbide diagram, there we use P plus F equal to C plus 1. Okay, there we assume the pressure of the system is constant. Therefore, instead of using the constant of 2, we just use the constant of 1. Okay, and that represents the temperature. Okay, so anyway, I'll give you that also in the next slide, but just for the sake of discussion, finish this part. So let's say I give you a system where you have only liquid water. So in that case, what is the degree of freedom? See, in liquid water, how many number of phases are there? Only one, because everything is liquid. F is the unknown. What are the number of chemically independent constituents? See, everything is water, so there is only one component, and plus 2 is as it is. So what is the F value here? F is 2. So that means you need at least 2 variables to define the state of your system, which is nothing but a liquid water. So in such cases, we use pressure and temperature to define the state of your system. Okay. Secondly, let's say I give you a mixture, okay, water plus water vapor. Okay. So in this case, can you tell me what will be the F value? How many phases are there in the system where you have water plus water vapor? 2, right? Because there is a liquid water and then there is a gaseous phase of phase of water vapor. So there are 2 phases. F is the unknown. Chemical composition is still 1 only, because water is also H2O, water vapor is also H2O. So they have same chemical composition. So that is 1, and the 2 is as it is in the end. Okay. So that gives you F of 1. Okay. That means you need only one of the variables. Okay. So basically, see, when does this happen? There is called as phase change dome, right? Where you have this, see, outside it will be all vapor, and inside it will be liquid plus vapor, right? If you consider the water vapor and liquid mixture. So basically, if your system has water and water vapor mixture, you need only one variable to define the state of the system. So that can be only pressure or temperature, because this equilibrium pressure and equilibrium temperature during the phase change of liquid water to water vapor or vice versa, they are interrelated, right? Equilibrium pressure and temperature. Because given corresponding equilibrium pressure, you will know corresponding equilibrium temperature. Okay, you must have seen that in your steam tables. Okay, So therefore, you only need one variable, either P or T. If you know one of them, you can identify that what is your system or the state of your system. Okay. And then there is, let's say, third example, where you have liquid water plus water vapor plus ice. Okay. So now, how many phases are there in this system? 3, right? And F is unknown. Chemical composition is still 1 because all of them are H2O, and the 2 is as it is, so that gives you F of 0. Okay, so that means, this is a fixed point. You don't have any variable that you can use to define this point. Okay, so it is a fixed point. Okay, and it is called as triple point of water. Right, and the triple point is fixed point where, and as per the definition, it is a point where all 3 phases coexist in equilibrium. Okay, that is the definition of triple point of water. And sometimes they ask you what is the temperature at triple point of water. So it is 0.01 degrees Celsius, or if you want to do it in Kelvin, it is 273.16 Kelvin. Okay, you have to remember these things because in one of the exams they had given you 2 options: 273.16, that was one option, and 273.15, that was also one option. So you should remember everything, okay, because these are very standard numbers. And not only that, you need to define the pressure also, because since this is a fixed point, temperature will also be a fixed temperature and pressure will also be fixed pressure. It comes out to be 611.97 Pascal. If you want to define it in terms of kilopascal, it will be 0.612 kPa. And sometimes they may ask you to find it in terms of mm of Hg. Okay, so that is 4.587 mm of Hg. Do you guys know how to convert Pascal into mm of Hg? No, huh? See, there is a famous relation. Okay, P equal to rho gh. This is famous statics, fluid statics correlation. So pressure, is 612 or 612 Pascal, let's say. So if you have to put 612 Pascal here, and since we are talking about mercury, the density should be 1360 kg per meter cube. Okay, this is the standard density of mercury. This is your 6.612 kPa P value. G is again 9.81 standard value, and then you will get H value. Okay, so can anybody verify what the H value that you get from this calculation? It should be around this one, 4.587. Okay, so that is how you calculate H. Okay, because you see this is mm of Hg, right? That means it is a parameter of some height. Okay, so that is nothing but P by rho g, and here we are using Hg, means mercury. Okay, so therefore we are taking the density of mercury, which is 13,600. Can anybody do this calculation? 612 divided by 13,600 and then divided by 9.81. Yeah, it is 4.587. Okay, yeah, it is in meters, so you have to convert it in mm. Okay, so these are some standard formulas. There is because this is just the pressure conversion, right? So nothing fancy is happening here. Okay, and then there are certain things about this thing, but I need more space. Shall I go to the next slide? So apart from the triple point values and degree of freedom 0 there, You should also note that, this triple point of water, is used as a reference point in steam tables. Okay, so some of you might have seen steam tables, not yet, then you should go and download them. But we use triple point as the reference point in your steam tables, and therefore you'll see that UF, which is nothing but internal energy of liquid water at triple point, SF, which is also a specific entropy of liquid water at triple point, and HF, all of them are considered to be zero at triple point. Okay, you can go and check in your steam tables also, because every steam table starts from 0.01 degrees Celsius. Okay, that is the reason, because that's the reference. Okay, and yeah, since we are talking about this triple point, you should also note that there is something called as critical point of water. Okay, because they sometimes ask some questions on this topic also. Okay, so the critical point of water, if you plot a pressure volume plot, and let's say this is your liquid vapor, this thing. Okay, so you'll have liquid plus vapor in this dome. Okay, and outside the dome you have just vapor. Okay, so the critical point is defined as the maximum pressure above which you will not observe liquid state. Okay, so if you go higher than this pressure, you will not get any liquid phase. Okay, you will always have vapor phase after the critical point, or at pressures higher than the critical point. Okay, so that is the definition of critical point, and the values are, at least for water, you should remember these values. It is 373.95 degrees Celsius temperature, and the pressure at critical point for water is 220.6 bar. Okay, you must have heard this term, which is nothing but nowadays very famous, which is called as supercritical boilers, right? Have you heard this term, supercritical boilers? Yeah, and basically they use this concept of operating above the critical point. Okay, Matisham, you have not heard, that's fine, you can just Google about it. So basically what they do, see, in a conventional boiler, you heat the water from liquid state, and then you keep on heating, it goes to superheated state, right? But in supercritical boilers, what they are doing nowadays is they heat it in such a way that liquid water instantly flashes to the vapor. Okay, so that it says that you need lesser fuel for that. Okay, but all those things are there, but basically they want to avoid this liquid to vapor phase change region, because there you have to put in extra energy because of phase change, because phase change is also associated with the latent heat of phase change, right? So therefore nowadays they directly heat the liquid water at room temperature in such a way that it will directly go to the supercritical phase. Okay, how do they do that? That's an interesting topic, you can look it up. Basically what they do, they follow this path. Okay, loosely speaking, they will follow this path for heating. Okay, they don't come in your liquid vapor phase change region. Okay, so they maintain pressure of your water at the start of the heating such that it will never come in the two phase region. I mean, two phase means liquid and vapor region. It will be directly flashing from liquid to vapor. Okay, but yeah, as far as your gate exam is concerned, you are supposed to remember these numbers. Okay, so this is about triple point of water, critical point of heat water. And since we are on the topic of Gibbs phase rule, I'll just give you one important note about that. Okay, shall I go to the next slide? Because sometimes students get confused. See, right now we are studying thermodynamics, so therefore you remember P plus F equal to C plus 2. But in material science, what happens? In material science subject, especially this iron carbide diagrams. If you'll study, some of you may already know this, but it is not usually known that there the Gibbs phase rule is given as P plus F equal to C plus 1. Okay. So it is not different Gibbs phase rule. It is the same thing. It's just that instead of 2 in thermodynamics, they use 1 in material science, because here the pressure of the system, that alloy system, is assumed to be 1 atmosphere or constant. Okay. And that is why you don't take 2 as the on RHS, you take only 1. Okay, so therefore there is a very famous question that these iron kite diagrams are, so that diagrams that you will study are valid only for atmospheric pressure. Okay, if you take this iron alloy, and let's say you take it to the moon where the pressure is different than the atmospheric pressure on the earth, you will not get the same iron carbide diagrams. Okay, so that is very important question. Many times they ask this question also, but that is not in thermodynamics, that is in material science subject. Okay, so these are some important topics about Gibbs phase rule. So shall we go to the next slide? See, we'll discuss some important things now. We have like half an hour, so we need to hurry slightly. Okay, shall I go to the next slide? Okay, so then there is important classification of various processes. Okay, so reversible process versus irreversible process. Okay, this also we use extensively during our discussions in thermodynamics. So first of all, it is defined in the context of reversible processes, and whichever process is not reversible is called as irreversible. That is the classic definition of way of defining these things. Okay, so the reversible process means if a system returns to its original state, without leaving any effect on the surrounding. Okay, such a process is called as reversible process. Okay, that is the definition of reversible process. And irreversible process means any process in which the system returns to its original state with having some impact on the surrounding. Okay, so in simpler words, all processes except reversible processes are called as irreversible processes. Okay, and there are some common sources of irreversibilities. Okay, so I need more space for that. So shall I go to the next slide? Okay, so since we are talking about reversible and irreversible processes, you should know there are some common sources of irreversible or irreversibilities in your system. Okay, we'll study about this when we study entropy topic also. But since we are doing some discussion on basics, you should remember these things, because these are also asked in many competitive exams. Okay, first is friction. So if there is a friction in your system, that process will always be irreversible. Okay. Second is called as free expansion. Okay, free expansion or expansion against vacuum. Okay, so famously this one example is given that you have this piston cylinder assembly. There is some gas here at certain pressure, which is, let's say, higher than the atmosphere, and then you evacuate this system from the other side of the piston. So that's why your P naught becomes 0 here. Okay, so there is no resisting force for this gas to stop expansion. Okay, so therefore such cases is also it is called as free expansion case, where you don't have any resistance for the expansion of gas inside the piston cylinder assembly. That is called as free expansion or expansion against vacuum, and it is always irreversible process. Okay. Then there are two more classical processes which introduce irreversibilities, or these are irreversible processes. Mixing of fluids. Okay, so if you mix two fluids, it is irreversible. You can separate them, but you need to spend a lot of energy to do that. Okay, so therefore it is a irreversible process always. And fourth is nothing but heat transfer to a finite temperature difference. Okay, this is also an irreversible process. Once it is done, you cannot reverse it without having any effect on the surroundings. Okay, we'll see these things when we study entropy. There is you can do some calculations of entropy also for these processes. But right now, since we are talking about irreversibility and reversibility or processes, you should know that these four processes will be always irreversible, whatever you do. Okay. Example of irreversible process. You can give any process having friction or any process having mixing of fluids. See, all these four processes are reversible process only. Second point, can you please explain? See, usually what happens in your piston cylinder assembly, if you have some gas, let's say gas molecules are there at higher pressure, they will always try to expand, right? So if outside pressure is equal to 1 atmospheric pressure, okay, so the gas molecules will do the expansion, and for that they have to do the work done against pressure of 1 atmosphere. But if there is no resistance, if the pressure outside the piston is 0 atmosphere, that means it is vacuum, or if you take this piston cylinder assembly in the space, in that cases the gas will expand, but it is not doing any work against any resistance. Okay, so therefore it will take up whatever space available. Okay, so that is called as free expansion. And since there is no resistance, okay, so therefore this process is irreversible, because if you want to make that gas or the gas molecules come back to the same volume after free expansion, you have to put extra work, right? And therefore this process is not reversible, it is irreversible. Okay, you cannot have zero impact on the surrounding during free expansion and reversal of it. Okay, is it clear? See, very good description on this 4 points is given in the PKNAG book. Okay, if you are not convinced here, you can read that topic in the PKNAG book. It is very well written. Okay, but since we are talking about this, I thought I'll give you everything in one place. Okay. Then before we move on to the next topic, you should know that when you have reversible processes, let's say this is your pressure volume plot. Okay, reversible processes are always shown on the reverse PV diagram as a solid line. Okay, this is your reversible process. Okay, whereas the irreversible processes, they are always shown by dotted lines. Okay, something like this. Okay. So this will be a irreversible process. Okay, irreversible processes are always shown by dotted lines or discontinued lines. Very famous irreversible process is something called as throttling process. So if you when you study RAC subject, you study VCRS, vapor compression refrigeration system, and there out of 4 processes, 3 are shown by solid lines, whereas the 4th process, which is throttling is nothing but flow of the liquid or gas or mixture through a restricted passage. Okay, so that is also always irreversible. So you can add the 5th process here also, throttling. Throttling is also irreversible process always. Okay. What is throttling? It is nothing but essentially flow through a restricted passage. But we'll deal about this in details when we study RAC, refrigeration and air conditioning. Okay. And then there is something called as quasi-static process. Okay. So there is one reversible, then is one irreversible, and in between there is something called as quasi-static process. Okay. So this is, this is not completely reversible and completely irreversible. Okay. Basically, if you see the PKNR book, they have explained it like this. Again, you have a piston cylinder assembly like this. Okay. There is some gas filled here at higher pressures, and you have certain weights on top of this piston, various different small weights. Okay. And what you do, you gradually replace, or you take it out one by one. Okay. So if when you take one weight out, the gas will slowly expand, but it will not have a large expansion, right? It will have very slow expansion. Okay. So here you have high pressure gas. Okay. And you keep on replacing or removing these small weights gradually, and then you wait for some time. After you remove one weight, you wait for some time, and then you let your system stabilize. Okay. And if you plot that on the PV plot, see, initially pressure was high, right? So it will be somewhere here, and then there will be different equilibrium states, and then you will reach certain final volume where you will have less pressure and more volume because the gas is expanding. So it is nothing but quasi-static process. Okay. So the quasi-static, as the name suggests, quasi means it is static means it is in equilibrium, but quasi means it is equilibrium in steps. Okay. So the quasi-static process means it is the locus of all equilibrium points, going from 1 to 2. 1 represents your initial state, 2 represents your final state. Okay. So you don't go from 1 to 2 very fast. You go very slow, and it is consisting of many small equilibrium steps. Okay. So that is what quasi-static process means. Okay. So many times when we can't consider any process as a reversible process, we assume it to be quasi-static process, and then we study that. Okay. So quasi-static means, like, we assume that equilibrium exists at each and every disturbance. Okay. Is it clear? See, these are some basic concepts. I mean, you can read more about them also if you want. In your PKNL book is very good for this. Okay. And before we move on to the next topic, I'll just give you one hint, because this is also asked in many competitive exams. Okay. Quasi-static process without friction is considered as reversible process. Okay, very important note, because see, sometimes they ask you what is the difference between quasi-static process and reversible process. In many cases, we neglect the friction and we say that quasi-static is same as reversible. But strictly speaking, in quasi-static processes, what you do is, since you are removing these weights slowly, one by one, your system goes from equilibrium state 1 to second equilibrium state, but in between there is some friction. Okay, but since you are going very slowly, the effect of friction is neglected. Okay, so therefore it is said that quasi-static process without friction is a reversible process. Okay, it is an important point for competitive exams. Okay. Arsini, the thing is, see, you keep on removing these small weights, right? So initially your piston will be here. Okay, let's say this is your starting point. Initially your piston will be here. When you remove another weight, your piston will go slightly high. Then you wait. You don't immediately remove the next one. You let your system come to equilibrium at this new location. Then you remove one more weight so that your gas will expand even more. Okay. So like that. Then you plot the equilibrium states, and if you join the equilibrium states, that gives you quasi-static process. And practically speaking, we do this in some finite steps. But quasi-static process means you have some infinite equilibrium steps in between. Okay, so therefore it is almost assumed to be reversible process. Okay, is it clear now? See, even if it is not clear now, since we don't have time, I would request you to go back and read this description in the PKNAG book. That is very well written there. Okay, because now we are almost at the end of the class and we need to take more. Two topics are there. Okay, you read up the PKNAG book. Next class, if you are still not convinced, you can ask me. Okay, so let's move on for now because otherwise we'll run out of time. Okay, so then two more topics are there. First is called as ideal gas equation. Okay, we use this also extensively. So you should know what is ideal gas equation. Okay. First of all, before using ideal gas equation, you should know what is ideal gas. See, PV equal to RT is incomplete. PV equal to nRT. Okay, N is also there. But before that, let's see what is ideal gas. Okay, so ideal gas is a gas which satisfies certain characteristics. First is no intermolecular forces. Okay, so within your molecules or atoms, there should not be any forces of attraction or repulsion. Okay, so that is called as no intermolecular forces. We consider them as point particles. Okay, and we consider this because we assume that volume occupied by molecules of the gas to be zero. Molecules of the gas to be zero. Okay, we don't consider the effect of volume. Okay, and then we assume that the collision between the gas molecules are perfectly elastic collisions between gas molecules. Okay, so if these three conditions are satisfied by any gas, let's say 1, 2, 3, then we call that gas as ideal gas. Okay, but in reality, it doesn't happen always. Okay, so therefore, in very specific conditions, what happens if you consider a real gas? Yeah, maybe this is first note, you should take it down. That is, real gases, real gas behaves as an ideal gas at low pressures. Okay, and why? Because at low pressures there are less number of molecules present in the domain. Okay, and therefore the intermolecular forces go down. Okay, that is why. So ideal gas, real gas behaves as an ideal gas at low pressures and at higher temperatures. Okay, at higher temperatures, the internal energy of gas molecules increase because temperature is representation of internal energy, and therefore their intermolecular forces of attraction reduce. Okay, so therefore real gases behave as ideal gas under only two conditions. This is very important. Okay, this has been asked many times, either at low pressures or at higher temperatures or both. Actually, it should be or here. Okay, or both also. Okay, and yeah, there is one more note. There is no space here. Shall I go to the next slide? Okay, there is something called as perfect gas. Okay, because in some places you may see that term also. See, the one property of your ideal gases is, this ideal gas, this Cp and Cv, which is nothing but specific heat at constant pressure and specific heat capacity at constant volume. They are function of absolute temperature. Okay, but this perfect gas is nothing but it satisfies all ideal gas properties. Okay, it satisfies all uh, all characteristics of ideal gas. Ideal gas, except this CPCV of perfect gas are assumed to be constant. Okay. Basically, that means they are not a function of temperature of the gas. Not a function of temperature. Okay, so that is the only difference between ideal gas and perfect gas. We use this perfect gas in many topics like power plant engineering, IC engines, etc., etc. Wherever you use Cp delta T as the expression for ideal gas, that means you are basically using perfect gas assumption, because if you are just using ideal gas assumption, Cp delta T is not valid because Cp is also a function of temperature, so it will be Cp of T into delta T. But in many places we use Cp delta T directly, mCp delta T, right? So there we are basically assuming that the gas is perfect gas because we assume Cp to be constant. And it is valid assumption, okay? It is not like very wrong, because for air and all, the Cp remains constant irrespective of temperature. For a very, very wide range of temperature, the Cp and Cv remain constant. So therefore, perfect gas assumption for air is not that irrealistic, okay? So this is about ideal gas and then ideal gas equation. So some of you told me, right, this is PV equal to nRT, right? This is your ideal gas equation. You should know certain things. This is always absolute pressure. Okay, do you know the difference between absolute pressure, gauge pressure? If you don't, I'll just give you one simple schematic so that you'll remember. Okay, so let's say this is your okay, so you have two references. Okay, so let's say this is your zero pressure. Okay, this is zero pressure absolute, and let's say this is your atmospheric pressure, which is nothing but 1 atmospheric pressure that we usually assume. Okay, so now if your system pressure is this, okay, so let's say P1. Okay. So there are two ways to define P1, right? If you measure this P1 from the absolute zero, this will give you P1 in absolute terms, right? But if you measure this P1 from your atmospheric pressure, it gives you P gauge pressure. That will be nothing but P1 absolute minus P atmospheric. Okay, so that is the difference between gauge pressure and absolute pressure. Okay, is it clear? So, there is a saying that, this absolute pressure is always greater than or equal to 0. But this gauge pressure at any point, if you want to calculate, it can be greater than 0, equal to 0, or less than 0 also. All three are possible. Because I can take some point here, right? So let's say this is my point, let's say P2. Okay. So here the absolute pressure is this much distance, right? So this is your P2 absolute. But your gauge pressure will be negative here because this will be your gauge pressure, right? P2 gauge. It will be negative because it is less than the atmospheric pressure. Okay, so therefore, this is how we calculate gauge pressure, atmospheric pressure, and gauge pressure and absolute pressure. Is it clear? You should remember the inequality. Absolute pressure is always positive. At the max, it can be 0. But gauge pressure can be positive, negative, or 0. So if it is above the atmosphere, it is positive. If it is subatmospheric pressures, the gauge pressure will be negative. Okay. So if you have understood, can you tell me what will be the gauge pressure for perfect vacuum? Can anybody tell me? The question is, what is the gauge pressure for perfect vacuum. First of all, do you know what is perfect vacuum condition? That is what I am asking, right, Bharat? Matisham, what is gauge pressure? See, perfect vacuum means, Harsini, is it 1 bar? Think about it. Think about the sign. See, perfect vacuum means the absolute pressure has to be 0. That is called as perfect vacuum. So now can you tell me, when your absolute pressure is 0, what is the gauge pressure? See, as I told you, you should start with always this diagram if you are getting confused here. This is your atmospheric pressure, right? Which is 1 bar or 1 atmosphere. So I am asking you, if I have a gauge which measures this pressure starting from this point. Yeah, so the answer is, it will always be -1 atmospheric pressure, because gauge pressure can be positive, negative or 0. If your system is at the pressures higher than the, see this is the atmospheric pressure, right? I'll just give you on this diagram only. If your system is operating at pressures higher than the atmospheric pressure, your gauge pressure will be always positive. At this point, it will be 0, because your atmosphere is equal to your absolute pressure. And whenever you're operating at vacuum conditions, your gauge pressure will be always negative. Okay. This will be taught to you in your fluid mechanics classes also later on, I think, but you should know at least this much for our thermodynamics study. Why? Because since we are studying ideal gas equation, in ideal gas equation, it is always absolute pressure, never the gauge pressure, okay? Don't make that mistake. This has been asked many times in previous year questions. Instead of giving you the absolute pressure, they will give you gauge pressure, and then most of the students directly put that value and then they make a mistake. Okay. So I'll give you the P absolute is nothing but P minus P ATM. No, P gauge minus P ATM. P gauge minus P ATM. Okay, so if P gauge is less than P ATM, 1 second, is it correct? No, it should be ulta, right? P gauge should be equal to P absolute minus P ATM. P absolute minus P ATM. Yeah, this is correct, because when it is greater than atmospheric pressure, gauge is positive. When it is less than atmospheric pressure, absolute pressure is less than atmospheric, gauge is negative. Okay. So remember this whenever they give you gauge pressure instead of absolute pressure. So that is about P. V usually you have to consider in the total volume of the system. Okay. Total volume of system. And N, anybody knows what is N? Number of molecules. No, Matisham, it's not molecules. No. For mass we use M, small m. This is number of moles. Okay, number of moles is different than number of molecules. Okay, and okay, maybe we'll go to the next slide because we need to explain certain things. Okay, so this PV equal to nRT. This is absolute pressure always. This is total volume always. This is called as number of moles. Okay, you should refresh your basic concepts, okay, because otherwise you'll make very simple mistakes in these cases. So number of moles means, is it is defined as, I think, at STP, standard temperature and pressure conditions, if your gas occupies 22.4 liters of volume, it is called as 1 mole of gas. Or if it is equal to 6.023 into 10 to the power 23, 1 Avogadro number of molecules, that is called as 1 mole. Otherwise, in many cases, see, basically if you have like 1 mole of air is usually equal to 29 grams of air. Okay. Similarly, 1 mole of oxygen, if I am not wrong, it is 32 grams. Okay. So please revise what is this mole concept. It is taught in very plus 12 also. Okay. So that is about number of moles. This R is called as universal gas constant. Okay. Anybody knows the value of R, universal gas constant? And what is the unit? Bharat, it is not 287 first of all. 8.314 is correct. But what is the unit? .314 kilojoule per mole. No, that is incorrect. The unit is joule per mole into Kelvin, because there is temperature also, no? And see, the last but not least, this T. Never forget, it is always in Kelvin. Okay, it is the temperature in ideal gas equation is always in Kelvin. Okay, never in degree Celsius. Never in degree Celsius. Don't make that mistake. Okay, many times students always forget and use degree Celsius directly. That is totally wrong. Okay, so this 8.314 joule per mole Kelvin, or in some books you will see it is kilojoule per kilomole Kelvin. Okay, so that is fine because you multiply by 1000 both numerator and denominator, so that is okay. Okay, so in some books you will see the unit as kilojoule per kilomole Kelvin also. That is also fine, but it should be kilojoule on kilomole. Okay, it should not be kilojoule at one point and then mole at the denominator. Okay, is that clear, Matisham? Don't make that mistake. Okay. Okay, so then the last thing, because we don't use this NRT wala formula everywhere, we use something called as PV equal to MRT formula most of the places, because here M is mass. Okay, so mass can be in kg or gram, depending on that you have to take the R value, and R is called as characteristic gas constant. Okay, so the R bar is universal gas constant, whereas this R is called as characteristics or characteristic gas constant, and it depends on each and individual gas. Okay, so it is, see, universal means it is the same value for any type of gas. Okay, but here this characteristic gas constant is nothing but R bar divided by molecular weight of the gas. Okay, molecular weight of the gas under consideration. So if you are considering air as the gas, okay, so for air, your R value comes out to be 8.314 divided by what is the molecular weight of air? I had just given you in the previous slide. It is 29 grams per mole. Okay, so if you divide it by 29, what do you get? I think this is what Bharat was mentioning, 287. Okay, but that will be if you divide it, it will get 0.287. That is nothing but kilojoule per kg Kelvin. Okay. So this is the standard value that we use for air. Okay. So these are the major things about ideal gas equation. And one last thing that I will give you. See, before we move on from this slide, it depends on the gas under consideration. Okay, universal gas constant is same for all the gases, all the ideal gases, but characteristic gas constant is function of the gas under consideration. Okay, so for air it is 0.287. For some other gases, depending on their molecular weights, the value will change. Okay, so we'll stop after this ideal gas equation today because we are running out of time. There are 2-3 small topics remaining, but we'll take those in the next class. But before we conclude, I'll just give you one hint or note, okay, because this mistake also many students do. We'll later on study these two-phase mixtures, okay, where you have, here you have vapor always. This will be liquid plus vapor, and this side you always have liquid. Okay, so let's say this is a for water, if you say. Okay. So you should know when to use ideal gas. Okay, first of all, never use PV equal to MRT or PV equal to N bar T in two-phase region. That is very important because these are ideal gas equations. These are not valid for two-phase regions. Okay, and since we are talking about ideal gas equation, in vapor region also, if you are operating under this condition where you are operating at ideal gas equation, can be used for real gases at higher temperatures. Okay, so many times I have seen if it is just ideal gas or gas, students use it correctly, but in some problems they trick you. Okay, so within the two-phase region you can't use ideal gas equation, you have to use some other equations which we'll see later. Okay, so with that we'll stop for the day. There were some two small topics remaining. Yeah, Matisham, this is actually I think this is the last moment change of plans, because I think fluid mechanics was started, but there is some issue with the faculty who was taking fluid mechanics regarding its availability or something like that. So that's why Dinesh sir requested me yesterday evening to start thermo. Otherwise, thermo was supposed to come later after maths. Okay. So at this point, I also don't know when is the next thermo class, but mostly it will be next week somewhere. Okay. So I think maths and thermo will run parallelly now, and fluid mechanics, I'm not sure what is going to happen there. Okay, so you may contact Dinesh sir about this, but at this point, I also don't have the schedule for next week. Okay. And in the meantime, I'll share the notes for this class, and if you are interested, you can download them. Otherwise, the class is over for today. We'll meet next time, and we'll start important things. This is just the basics. Okay. Today, no maths class. No, Bharat. There is a maths class in the night, 9 to 11. So that is there. That's a problem solving session. So that is also there. Okay. Okay. So next class we'll start important stuff like first law, zeroth law, work interactions, all those things. Next maths topic, Natisham. Let me just check. See, main things we have covered in maths, right? Linear algebra, calculus, probability. Last year we took, after this, we took vector algebra or vector calculus last year. Most likely we'll do that only. I'll just confirm once with Dinesh sir, because I think for the rest of the maths topics you need to make groups branch wise. So most likely vector calculus, but I'll check with Dinesh sir once, and we'll let you know about the next maths topic. Okay, so the slides are shared for this class. You can download them if you want, and we'll continue from here next class. Okay. In the meantime, you should see these are all basic concepts. Okay, so if you want more understanding or deeper understanding, we can't take everything in the class because it will take a lot of time. So just read PKNAG book. It is good for these topics. Okay. So if any doubts, you can ask me. Otherwise, we'll stop. Okay. Shall I close the class? and see you next time. Okay, yeah. Thank you and see you tonight if you are in there for maths class. Okay, bye.